Today's speaker is Dr. Oğuz Gezmiş. He obtained his PhD from Texas A&M University in 2019 with a dissertation titled Special Values of L Series over Theta Algebras under the supervision of Matthew Papanikolas. Currently, he is working at National Tsinghua University. And let's welcome Dr. Oğuz Gezmiş for today's talk.
Thanks a lot for the introduction, and I would like to thank the organizers also for giving me this chance to talk about my recent work. And so today I'm going to talk about the Drinfeld modular forms of higher rank and quasi-periodic functions. And before I start, I should say this is a joint work with Yen-Sung Chen from National Tsinghua University. And for interested audiences, they can reach the paper, the preprint from that archive code. And I will just, I think this will be available after the talk in the website, so you can also go ahead and look at it. So, okay, so let me start from some classical story that we all know about the modular forms and that we're all familiar with. So H will stand for the upper half plane. And I will define the modular form of weight K for SL2Z. I will talk about only for the full group as a holomorphic function from the upper half plane to the complex plane, satisfying these two conditions, which are, the first one is a automorphic condition satisfying that property. So you have an action of SL2Z on the complex plane, and this is given in this way. And this will be equal to that product for any gamma in SL2Z and Z in the upper half plane. So the second one is the holomorphy condition at infinity. And this will be defined as follows. You set your Q as e to the 2 pi I Z, and the Q expansion of F will be of this form, starting from the non-negative indices and with the coefficients in the complex plane. Okay, these are the two conditions of being a modular form. And we will further call such function as a cusp form if this Q expansion starts with A1. Or maybe I should say, if the first coefficient is 0. Okay, so in this case, we will call them as cusp form. So let me just, after this definition, let me just go through a basic example of the modular forms. So for some convergence issues, you choose your K as a positive integer bigger than 2 and consider this Z lattice generated by this element Z and 1, okay, for Z in the upper half plane. And the Eisenstein series, GK lambda Z, will be defined by the sum of these reciprocals when M and N are not both equal to 0, okay? So it's a modular form of weight K when K is even and identically 0 if K is odd. And furthermore, this is an example of modular forms, but we will stick on the one which is normalized, and I will call it as this notation. And the reason for normalization is to get a nice Q expansion for the Eisenstein series here. And this is normalized by considering the Riemann zeta value at this integer K, so that this Q expansion will be given in this form. And this sigma K minus 1, what I mean by this function is taking N to its, the power of, the K minus first power of its positive divisors. And BK will be the kth Bernoulli number, okay? So this is just the one basic example of modular forms, and I will use them later on to define a function which is important for our consideration. So let me go through that. So the discriminant function, delta, is a function from upper half plane to C. We will define it in this way, okay? And it's a non-vanishing function on H, and it's also a cusp form of weight 12, okay? So these are already in the known. And we will define now the false Eisenstein series as a function from upper half plane to the complex plane, given by the logarithmic derivative of the discriminant function, all right? So this is given in this way. And we know more about this sort of function. Basically, we have the Q expansion of it, which says that it's holomorphic at infinity, and this is given in this with this rational coefficients. All right. So once you have all these, I will move on to the next property of the quasi-Einstein series is as follows. So they are actually quasi-modular forms. They are classified as quasi-modular forms. This notation, this terminology is due to Kaneko and Zagier, and it satisfies this functional equation given here. It's a bit different than the functional equation satisfied by modular forms. You have this extra term here, and this sets for any gamma in SL2Z, right? So then what we know about these functions are, this function is a bit interesting. Due to Deligne and Katz, we have this result. So you have your Z in upper half plane, and eta 1 and eta 2 be the quasi-periods of the elliptic curve corresponding to that Z lattice generated by Z and 1. So it satisfies this Legendre relation given in this way. Then we have that property. We have that this quasi-Einstein series can be written as some multiple of your quasi-period. Okay, so this is a nice relation between the quasi-Einstein series and the quasi-period you have. Okay, so the another one is about some transcendental properties of some special values. So you take your Z in upper half plane, but this time is a CM point, or you can think of this as an imaginary quadratic. And this is also, let's assume that this is not a zero of this quasi-Einstein series. Then what we know due to Zhang in 2012 that this value is transcendental over Q. Okay, so these are the properties that I will discuss to motivate the results I'm going to produce here. I'm going to introduce here, and I will move on to the function field setting now. But before that, let me ask: is there any questions so far? Okay, so let me now, this was the classical story. Now let me pass to the function field setting. And before that, let me introduce some notation, which will be in use throughout the talk. So P will be the prime number, and FQ will be the finite field with Q elements, and Q is a power of P. A will be the polynomial ring in theta. Theta is a variable, and with coefficients in FQ. Okay, so this notation is for, okay, so this is the definition of A, but the reason why I write Z here is to let you think that this will be the analog of Z in the classical case, okay? So you may think A replacing Z in the analogous structure in the function field set, okay? So similarly, I will define A plus, this notation for the set of monic polynomials in A, and this will stand for an analog of the natural numbers. So K will be the fraction field of A, or in other words, that's how we denote it. And this will be taught as the analog of Q. Now I will fix a notation for the absolute value corresponding to the place at infinity. It's going to be normalized so that the norm of theta will be equal to Q. Okay. And now I will make a completion of K with respect to that absolute value. And this will be given by this formal Lorentz series ring. And I will denote it by K infinity. But you may see this is analog of real numbers in this setting. Lastly, I will define the C infinity, and I will take the algebraic closure of K infinity, a fixed algebraic closure of K infinity, and then I will complete it. And this will be denoted by C infinity. Okay, and you may think this as this algebraically closed field as the analog of C. Okay, so this is the notation for the talk. Most of the time I will use them without recalling it. And these are the left-hand side will kind of give you an idea what kind of analogy we should expect. Okay, so the next objects are going to be the Theta algebra. So the Theta algebra is due to Tate originally in 1960s, and I will define them now, and I will say something more about them later. So let T be an independent variable over C infinity, okay? And we define the Theta algebra by the set of this power series in T, whose coefficients in C infinity behaving this rule, that their norm goes to 0 as the index goes infinity, okay? So this is the set of power series. We see them as the set of power series behaving this rule. But there is also another way of seeing these elements. We will also see these elements as set of holomorphic functions in the rigid analytic sense on the closed unit disk D. What I mean by the rigid analytic sense, I will consider the rigid analytic spaces when I'm considering the modular forms. And this will allow us to do nice analysis that doesn't exist due to the nature of this non-Archimedean norm. Because if you just consider the non-Archimedean norm, then your space will be disconnected and you need to have a nice connectedness properties. And for that, we are passing to the rigid analytic spaces, which are due to Tate in 1960s for his attempt to uniformize the periodic elliptic curves for the bed reduction, if I'm not wrong. And yeah, so these are the basic objects we are going to use, the Theta algebras. And whenever I say during this talk holomorphic functions, I mean holomorphic functions in that rigid analytic sense. I mean, we have our rigid analytic spaces. You can think of them as the local ring spaces. It has a Grothendieck topology structure on it, together with a structure sheaf. And with this spaces, we'll consider these holomorphic functions in that sense. All right. Okay, so now, as I say, we can see them as values as well, like just power series itself. And now I will define a norm on it. And I will define this Gauss norm by setting for any G in the Theta algebra by taking by defining the norm by taking the maximum of the norm of Ci when I is a non-negative integer. And this will be a maximum due to the definition of being an element in Theta algebra. But we know more that like this is a nice norm which makes T complete, which makes it a Banach algebra. Okay, so these are the properties that we need for the Theta algebras. And for the elements in the Theta algebras, we have also some operations that we can apply. That, okay, so you take your G as an element in T, and J is an integer. We define the J-fold twist of G by taking G and raising its coefficients to their Q to the J power and leaving T as invariant. Okay, so this will be an element in T as well, of course. And this is how we define the J twist of an element in the Theta algebra. So I will define another element and I will discuss this element in two ways, as value and as a function of T. Okay, so let me go through it. So first of all, this notation is going to stand for this fixed Q minus first root of minus theta. And the Anderson-Thakur element will be defined by this product of this fixed Q minus first root of minus theta times this infinite product of these reciprocals. Okay, so as a value, we know that it's unit. So you can find the inverse of it in the Theta algebra. But as a function, okay, before that, let me say that as a function, we can think of this as a function of T. And as a function of T, it's a meromorphic function whose poles at qt powers of theta. Okay, but you can do some trick to avoid these poles. Basically, the trick comes with this J twists. So, and we will define an important element pi tilde in C infinity cross by taking the first twist of omega and then evaluating at T equals theta. Okay, and this will be given by this times this infinite product, and this will be a useful element for our results. And this is basically how we define it. So you use the properties of this omega as a function of T, and then evaluate it, and then you get your pi tilde. Okay, so these are some important elements we will consider. Now, okay, so now let me go through the A lattices to understand the Drinfeld modules better. So first of all, an A module M, we will say it as a strongly discrete A module if the intersection of M with any ball of finite radius is finite. And we will call an A module M to be an A lattice if furthermore it's free and finitely generated and strongly discrete. Okay, so this is very natural to define or to define an A lattice. And now we will talk about the category of these objects. And first of all, let me define the morphisms. So two A lattices, lambda and lambda prime, will be isogeneous if there exists an element C here, satisfying these two properties. First, C lambda stays under lambda prime, and the quotient will be a finite A module. Okay, so as naturally, we will call this C as an isogeny between lambda and lambda prime whenever it exists. And moreover, if you have this fact that if C lambda is equal to lambda prime, then we say lambda and lambda prime are isomorphic. Okay, and now I will briefly mention that the set of A lattices of rank R forms a category, and we will have these morphisms to be isogenies defined here. Okay, so now in our hand, we have the category of A lattices. So let me move on to the Drinfeld A modules now. Okay, so the Drinfeld A modules I will define as follows. But before that, I will define the power series ring as this non-commutative ring with respect to that condition that tau C is equal to C to the Q tau when C in C infinity. And as you see that it's non-commutative with respect to that rule. And I will define C infinity tau to be the ring of polynomials in tau. And tau will be a variable now. And these are the two definitions I'm going to use, C infinity tau and this power series ring. Okay, so now I'm ready to define the Drinfeld A modules. So the definition of Drinfeld A modules is certainly more general than this. You don't have to stick on A to be the polynomial ring. But for our concerns, I will define it in this way. So R be a non-negative, the positive integer, and a Drinfeld A module phi of rank R will be an FQ algebra homomorphism from A to C infinity tau, uniquely defined by the value of theta. Okay, so you can define your Drinfeld A module whenever this homomorphism takes phi, takes theta, and this will be, let me denote it in this way. And we also have one more condition that the art coefficient of the tau art coefficient should be non-zero. Okay, so you have your homomorphism. It has an image inside here, and its art coefficient should be non-zero. Okay, in this way we call them as Drinfeld A modules. And one example is the Carlist module. So you may say, why do we define it? Why do we call it as Carlist? Because interestingly, like maybe 40 years ago, 40 years before Drinfeld defined such objects, Carlist was doing this work arithmetically, and he used these objects also in to do some class field theory for the function field setting. And for that reasons, we are calling that specific Drinfeld A module of rank R as Carlist module. And this is defined as follows. You have your homomorphism sending theta to theta plus tau. Okay, so I will recall this later. And this is a relation with this pi tilde I defined earlier. And moreover, maybe this also motivates why we call them as module, that phi gives an A module structure on C infinity defined as follows. You have your A in A and Z in C infinity. And we will define this phi AZ as taking Z to that element. Okay, so the phi A has an image under this homomorphism phi, and then you are acting Z on this image. And as you see, this tau now is going to act like a Q power Frobenius. And this is how we define the action. And by the property of this Drinfeld A module, this will give you a non-trivial A module structure on C infinity. What I mean by non-trivial, this does not come from just left multiplication of A with Z. All right. So these are some basic properties of the Drinfeld A modules. And now I will discuss the next objects, the next objects, which are called morphisms between Drinfeld A modules, to be able to say something about the category. And here it goes. So the set of Drinfeld A modules forms a category, and the category, or this morphisms of this category, will be given by these elements U, which are morphisms. But what I mean by morphism between these two Drinfeld modules is just a non-zero element here, satisfying that relation in C infinity tau. Okay, so these are going to be called the isogenies or morphisms. And as usual, if it has no tau term in it, if it is just an element in C infinity cross, then we say phi is isomorphic to psi. Okay, so, and we will also define the endomorphism ring of phi, just like what we do for the elliptic curves. And we will define these elements to be the set of elements phi satisfying that relation. Due to Drinfeld, we know that it's a commutative ring and it's free and finitely generated A module and whose rank is bounded by R. And this tensor also forms a field extension of K of finite degree. And the degree is also bounded by the rank in our setting. And we say, moreover, we say that phi has complex multiplication, or we shortly say CM, if the dimension of this tensor over K is R. So the interested reader on elliptic curves will be, interested audience on elliptic curves will be probably notice the analogy here. If this rank is full, if this dimension is full, then we call them as CM Drinfeld A modules. Okay, so that's kind of going into the same way as in the analogy between the CM elliptic curves and CM Drinfeld modules. But in this case, you have more flexibility. You can define Drinfeld A modules of any rank. Okay. So now the other structure is the exponential function of the Drinfeld A modules. So you have your Drinfeld A module, and the exponential series can be given by this infinite series in this non-commutative power series ring with respect to these two conditions. First, the first coefficient we are letting it to be 1, and it respects that relation in this power series ring. Okay, so this is called the exponential series, and this exponential series will induce a function from C infinity to C infinity, taking z to that infinite series for all z. So the convergence issues are thankfully no problem. And since your exponential series respect that rule, using that property, you can show that actually this function converges for any values of c. Okay, and we are also interested in its kernel, and each element in the kernel, this function, it's an F-linear function, is called a period of phi. Okay, we will call any element as period. And it has an A module structure, and the A module structure is pretty simple. It's just left multiplication. But the reason why it forms an A module structure comes from, again, this quality. Okay, and furthermore, it's an A lattice of rank R, and we call the kernel of exponential phi as the period lattice of phi. Okay, so simply we can say that instead of time to time, instead of repeating kernel of exponential phi, I will just say the period lattice of phi. Okay, so now I will introduce why are we interested in A lattices, and then define the Drinfeld A modules in this slide. This is because there is a correspondence between these two categories. And this correspondence will be very useful to define further objects in the function field setting. So let me discuss briefly how this correspondence takes place. So there is an equivalence of categories between the category of Drinfeld A modules of rank R and the category of A lattices of rank R. And here it goes. So you have your lambda as an A lattice of rank R. And there exists a unique Drinfeld A module phi up to isomorphism, so that it's exponential function given by this Weierstrass product expansion. And as you see, the zeros are explicitly the elements of this lattice, and we call phi to be the Drinfeld A module corresponding to lambda. Okay, that's one way. And the other way, you start with your Drinfeld A module, and then you consider its exponential function, consider its kernel, and then this kernel, which is an A lattice, will be the corresponding A lattice for your Drinfeld A module up to isomorphism. Okay, so maybe to give an example might be useful. So remember the Carlist module that I mentioned earlier, taking theta to theta plus tau, and it's a Drinfeld A module, and the corresponding A lattice is a lattice of rank 1 generated by this element pi tilde we talked earlier. I already stated in the previous slides, but I just want to repeat again. And that's the correspondence for the Carlist module. So that's why this pi tilde is somehow important for the Carlist module. And also, surprisingly, this is also appearing in many other places when we are talking about further objects in this setting. Okay, so any questions so far about these objects? All right. So let me talk about the phi biderivations now. So the name and the idea is to seek some drama isomorphism analogy as drama isomorphism. Sorry. Any question?
Yes.
Yeah.
Why is the exponential function called the exponential function? Is it does it have anything to do with exponential function in the sense of, say, Lie algebra settings, or the usual more familiar exponential function?
Yeah, actually, it's a great question. This is actually kind of related to the analogy with the elliptic curves. So you may have a short exact sequence having the period of the elliptic curve and the other objects corresponding to the elliptic curve, and the exponential function is the function given by the Weierstrass-B function and its first derivative and 0. So with this exponential function, you have a short exact sequence, and you have the same short exact sequence. If you think of this exponential function in this case, you have your period lattice, and you have your exponential function whose kernel is the period. And in the same, we now have the same analogy with the elliptic curves case, actually. So my answer to that will be, this comes from the analogy in the elliptic curve case. So yeah, I think that's what we are calling them, exponential function. But that's a great question. Yeah. Okay. So now let me move on to the next slide. So phi biderivations will be defined throughout. So it has been defined throughout the seek of some kind of analog of the drama isomorphism happening in the elliptic curve case, and for this purpose, we were seeking for some analog of the drum module and the first basic homology group. And for these purposes, due to the work of Anderson, Deligne, Gekeler, and Yu, we are able to define these phi biderivations. And before I give the definition, I just want to say that these phi biderivations, up to some equivalence condition, that they are elements of this drum module in the function field case. So you may see them as this analog of the differential forms. And let me go through the definition. So you have your Drinfeld A module of rank R, sending theta to that element as before. We define a phi biderivation as a map from A to that ring, satisfying these following properties. First, it's an FQ linear map, and it respects that rule. So you state eta C as the image of C under this map eta, and it should satisfy that property for any C for any A, B. Sorry, it's a typo. A, B, for any A, B in A, we have this property. Okay. And one example is that the FQ linear map delta naught sending A to A minus phi A is a phi biderivation you can show. And the second example we are interested in, for J between 1 and R minus 1, the FQ linear map delta J sending theta to tau J is also a phi biderivation. Okay, so these are the biderivations we will be interested in. And with these biderivations, we will define the quasi-periods. But before that, let me discuss the another objects attached to Drinfeld modules, or in particular the biderivations called quasi-periodic functions. So you have your eta, a phi biderivation, and there exists a unique function from C infinity to C infinity satisfying that functional equation. Okay, and we call this function the quasi-periodic function corresponding to eta, and it's an FQ linear function. And moreover, this is actually for any value of C in C infinity, this is actually convergent in C infinity. Okay, this is an entire function. And the uniqueness comes from solving this functional equation. And one example is that, remember this delta naught I defined taking a to a minus phi a. The corresponding corresponding quasi-periodic function to that will be the function sending z to z minus exponential phi. So this is just one simple example of that sort of functions. But remember, I defined several other biderivations here as well. And we may wonder, what are the quasi-periodic functions corresponding to that biderivations? Well, in this case, we don't have a nice, so you may come up with some series expansion for these quasi-periodic functions, but what we are interested in are the values of these functions at periods. And for this purpose, I will define the Anderson genetic functions to understand the values of that quasi-periodic functions on the periods. Okay, and the definition is as follows. You have your phi, Drinfeld module, and exponential phi given in this way. We define the Anderson genetic function as phi zt by this infinite sum, and the coefficients are these values of the exponential function, and they are power series in t. So the properties of this exponential function, it's nice convergence properties will allow you to show that it's an element in t, okay? And due to Pellerin, you can do more. You can see this function, you can see these elements as this infinite sum of these ratios, okay? And for a fixed z, what are we saying they are Anderson genetic functions? For a fixed z, you can even see these functions, you can even see them as functions in t. And for this fixed z, this will be metamorphic functions whose poles at qt powers of theta, okay? And by Pellerin, we have this following result, which will be useful. So you have your j between 1 and r minus 1, and your f delta j be the quasi-periodic function corresponding to that phi biderivation delta j. Then, for the values of this quasi-periodic function at the periods of the Drinfeld module, you have this property. So you have this value, but you can write this value first, taking the j twist of your Anderson genetic function and evaluate at t equals theta. And if you want to write it explicitly, you can write this in this way. Okay. So in other words, there is a nice relation between the Anderson genetic functions and the values of this quasi-periodic function at the periods. Okay. But we have in the literature, we have a terminology for such values. For any lambda, for any period of phi and j between 1 and r minus 1, we call these elements as quasi-periods of phi. Okay, so this will be the terminology we are going to use. Okay, so far what we have is periods, quasi-periods, and our Drinfeld module, and the correspondence of it with the A lattices. So before I move on to the next slide, is there any question? Okay, so now let me just start talking about the Drinfeld upper half plane. So from now on, we will set R to be a positive integer bigger than or equal to 2. And I will define the Drinfeld upper half plane as omega r, which is just a set reference. You have this projective space with C infinity coefficients and take out all the K infinity rational hyperplanes. And it is a rigid analytic space, okay, just like in the sense that I discussed 5 slides ago. And it's actually a connected rigid analytic space. And this will be useful because now we have the connectedness. But let's just go to another identification of omega r. And let's see these elements as these column vectors, okay, whose entries are K infinity linear independent elements, because we are taking out all the K infinity rational hyperplanes, so we can do that. And we do a normalization so that the last coefficient will be equal to 1. Okay, so whenever I say an element in omega r, this is what I mean. So time to time, I will just keep writing ZR just to see how things are functioning. but I don't mean anything else. I still mean ZR to be equal to 1, but just some notational purposes, I decided to write ZR instead of writing 1. But as I say, this is going to be the case for the rest of the talk. Okay, so for a given Z in omega R, we will set the Z tilde by just forgetting the first coefficient, first entry of Z. And this will be an element in omega R minus 1. Okay, and we will define some certain lattices. And this is how we denote them. So you have your C, and you have the CZA and CZ tilde A will be the lattices generated by the entries of CZ and CZ tilde, respectively. The first one will be a rank RA lattice, and the other one is rank R minus 1. And what I mean by CZ is just like multiply all the entries by C, with C. Okay. So as we see before that, there is this correspondence between the A lattices and the Drinfeld A modules. Now you have an up to isomorphism. You have a Drinfeld A module phi Z, and you have a Drinfeld A module phi pi tilde Z tilde. We will denote them like this, and the first one will be the Drinfeld A module corresponding to ZA, and the second one will be the one corresponding to pi tilde Z tilde. Okay, so this is the notation we are going to use. And lately, let me denote UZ as the value of exponential phi pi tilde Z tilde at pi tilde Z1, and take the reciprocal. And this will serve as the analog of Q in the function field setting. It will be parameter at infinity. And this value will not be 0 because this kernel has the elements here. And this is not an element in this kernel due to the fact that the entries are linearly independent. Okay, we will keep this in mind when we talk about the modular forms. So let me pass to that by first defining the action of GLRA. And this is how we define the action. So you have your gamma given in this way, and we define the action of GLRA on omega R by taking Z to that element. So let me explain what are those. So as you see, this is so if you do a matrix multiplication, multiply gamma with this column matrix Z, the first entry will be this one, R minus first entry will be this one, and Rth entry will be this one. And to respect the normalization we used earlier, we are just dividing everything by the Rth entry of this matrix multiplication. But there is no problem with that. This will not be 0. And this is an element in omega R. And if we set, we are going to also set this J gamma Z to be an analog or to be a factor of automorphy in this setting. And it's an element here. So now we are ready to say something about the weak modular forms. And basically we are defining them. They are the holomorphic function, again, in the rigid analytic sense. A weak modular form, this function is going to be called a weak modular form of weight K and type M. So you need to have the type taken into consideration for GLRA. Again, I'm talking about the full group. If it satisfies that automorphic condition, F gamma Z will be J gamma Z to the K, determinant gamma minus M times FZ for any gamma in GLRA and Z in omega R. All right. So this is what we mean by the weak modular form. Now, what we know about the analog of holomorphy at infinity. This is a technical topic. I will try to be down to earth as much as I can. And so the result due to Passon, Brouwer, and Pink, they show that for any weak modular form, there exists a uniquely defined holomorphic functions here for each n, such that this series converges to FC on some neighborhood n of infinity. So you may think of these neighborhoods of infinity as the open, some certain open balls, the infinite union of some certain open balls with admissible open sets of omega R minus 1. Okay, so for such kind of sets are called to be neighborhood of infinity, but to this result is about convergence of this infinite series for some neighborhood of infinity. So once you have nice neighborhood of infinity, then this result this result, that will be the conclusion of this result. And such an expansion is going to be called the U expansion of F. So I will be more specific about this, because this neighborhood of infinity is just some domain of omega r. But by the abuse of notation, actually, I will time to time say FC is equal to that, because like if the FC by the connectedness of your omega r will be determined by the values of this infinite sum. So there is no harm to using slight abuse of condition to say FC is equal to that one. And such an expansion, again, will be called as a U expansion of F. We actually, I didn't notate it here, but we actually know more about these functions Fn. They are also big modular forms, but I will not talk about this now. But one more thing I need to say, that when r equals 2, there is an ambiguity of the definitions, because I start with r to be a positive integer bigger than or equal to 2. And what that means is not clear. So when r equals 2, these are going to be just constants, okay? Constant functions. But I will actually go back to rank 2 setting, and I will say, I will try to make things more clear, because the rank 2 setting was the first setting of Drinfeld modular forms in the literature. And that will be also useful to see the analogy between the classical case. Okay, so this is what we mean by this is what we want to say about Basson, Brouwer, and Pink result. And from all these results and the definitions we have, we are ready to define what we mean by the Drinfeld modular forms. A weak modular form of weight k and type m will be called a Drinfeld modular form of weight k and type m, again for GLRA, if F has a U expansion of the form, which means that, again, you have a nice neighborhood of infinity, so that the right-hand side converges to Fc, okay? And furthermore, just similar to the classical case, that we say that F is a Drinfeld Cos form if this first function you have is identically 0. Okay, so before I move on to the examples, I will say something about the history and the people who contribute to the theory. So first of all, the Drinfeld modular forms were introduced by David Gauss in his PhD thesis around the late 70s for the rank 2 case, because this was the closest to the analogy between the classical case and the function field case. But later on, using the work of Haberli, Kapranov, and Pink, Basson, Brouwer, and Pink were able to define Drinfeld modular forms of higher rank, both algebraically and analytically, so that we have a nice theory of Drinfeld modular forms anymore. And yeah, so this is and there are other people who are contribute to the theory, of course, like Eckler. There's a lot of work on that. And yeah, but the main parts of the analytic theory and algebraic theory, and to be able to connect these two, the work of Haberli, Kapranov, and Pink were very important. Okay, so now let me pass to the examples of the Drinfeld modular forms. So let me start from the type 0 case. So you have your Eisenstein series, just like in the classical case. And again, so you see that, remember the definition of the Eisenstein series, you had Z here. Now we are replacing it with A, and we are taking this infinite summation of these reciprocals, okay? And this will be actually a modular form of weight K and type 0 by some arithmetic properties of your finite field. That some of the modular forms of some certain case will not even exist. They will be identically 0, just like in the classical case, but I will not discuss this now. I will just try to give some examples. And the other example is coming from the definition of the Drinfeld module. So remember this phi z, the Drinfeld module corresponding to that lattice ZA. And for each I between 1 and r minus 1, you can define a function from omega r to c infinity, sending z to giz. And it's actually a modular form of weight q to the I minus 1 and type 0. Okay, these are called coefficient forms because they come from the coefficients of the Drinfeld A module. All right. So the next one is the discriminant function. Just like you will recall, you will remember the analogy and the discriminant function we have in the classical case. Those will be the functions defined by taking z to delta rz, and they are actually non-vanishing holomorphic functions because of the condition of being a Drinfeld A module. Remember, so the last coefficient should be non-zero. And indeed, it's a Drinfeld cusp form. It's a cusp form of weight q to the r minus 1 and type 0. Okay, these are the basic examples of the Drinfeld modular forms, which we can discuss for the full group. But you may wonder, is there any other? Because we have this type thing going on for this kind of modular forms. So is there any modular form of type 1, for example? Luckily we have, and it's called the H function of Gekeler. Let me briefly say something about how it's constructed. So you have your S, be a set of representative of the quotient space given here, and consider this set as given with these elements. These stars will stay for the elements of FQ, and you have your Z here, and for any U in S, we will define these series, okay, and we will denote it by this, and then we define the H function of Gekeler for rank R, given by this product times the Q minus first power of minus theta multiplied by minus 1. This definition is due to Gekeler. Actually, he defined it in the rank 2 case as an instance of Poincare series. And he also defined them for the higher rank in an unpublished work. And what we know about these functions is important. And this is as follows, that it's an unfinished Drinfeld cusp form, and its weight q to the r minus 1 over q minus 1 and type 1. Okay, so it's a cusp form, and in the theory we actually know that the other. So if you have a Drinfeld modular form of type non-zero type, then it should be a cusp form. Okay, so this is the definition for such functions. So before I move on to the rank 2 case and to make things a bit more specific, is there any question? Okay.
I have a question. Is there
Yes.
Functional equations like for elliptic Eisenstein series in the usual case for this Eisenstein series? Like functional equations comes from factors of automorphy.
So the functional equations, I know for the Eisenstein series, I don't know if they can be standing for the analog of that case, that there is a relation between the Eisenstein series and the coefficients of the exponential function, and also these coefficients. So you can actually relate the Eisenstein series to them or to the coefficients of the exponential function as well. So this is the functional equation I know about the Eisenstein series in this setting. So is this somehow, you think, related or?
Yeah, sure. Yeah, thanks.
Okay. Yeah.
Thanks, nice.
Mm-hmm. Yeah, I mean, actually, these kind of relations were also useful to prove our results. I'm not going to discuss them, but yeah, I mean, but there is some sort of subtle point of the Eisenstein series in this case. So you have para-Eisenstein series, and if I'm not wrong, the para-Eisenstein series are referring to the Eisenstein series coming from this coefficients of the exponential function, because you may somehow think of them as the Eisenstein series as well because of this relation that I just said. And this distinguish this differences has been made by Gekeler a few years ago. But the thing I want to say is, in this respect, it's a bit different than the classical case. Okay, so thanks for the question. And okay, so let me go to rank 2 case. Okay, as I say at the end of definition of the Drinfeld modular form, these objects were available for the around 1980s, and there were a lot of research appeared with respect to that Drinfeld modular forms. Let me just briefly discuss them, because they are also useful to understand what I'm going to introduce later, what I'm going to generalize. And for this respect, I will first talk about that kind of modular forms. So this omega-2 will be our main interest in the setting of rank 2. But because of this definition of omega-2, you can actually identify them as the set C infinity minus K infinity, because you have now two entries. One entry is 1, and the other entry should be K infinity linearly independent than 1. So then you can actually relate all of your elements to that, identify all of your elements here to the elements here. And once you do that, you'll see the analogy between omega-2 and the upper half plane, because as I said before, like C infinity kind of stands for the analog of complex plane, and K infinity stands for the analog of real line. And in this respect, you have this analogy right after. And now let me say Z as an element here, and phi Z be the Drinfeld module corresponding to that lattice generated by Z and 1. And I'm not defining anything new. I'm just repeating this definition of modular forms for this rank 2 setting, just to show the analogy. So you have the definition is that the Drinfeld modular form of weight K and type M is this holomorphic function, satisfying this following property. You see, so you have this, now you can interpret this action of GL2A on C infinity in omega 2, or that set difference, in this way. This is exactly the same notation wise. It's the same as in the classical case. And this will be this product for any gamma in GL2A and Z in this omega 2, or that set difference. And we recall that, so this will be our parameter of infinity right now. I define the parameter of infinity by just considering the exponential function corresponding to pi tilde Z tilde. But in this case, Z tilde will be just having 1. And then the Drinfeld module corresponding to this lattice pi tilde A was the Carlist one. And this is the exponential function of the Carlist module, evaluated at pi tilde Z and take the inverse. And the U expansion of this Drinfeld modular forms should be of the form written here with the non-negative indices, and Cn is in C infinity. Again, this is an abuse of notation. This will converge for some nice neighborhood of infinity. Okay, so but I already discussed this. All right, so this is the definition, and you can easily see the analogy between the classical case and the function field case. And with this analogy, you may expect that some functions can also appear, like false Eisenstein series. And the Gekeler was the one who considered this first. So you have your discriminant function delta 2. So I define delta R, but now you replace R with 2 and then define everything in the same way by considering this identification between omega 2 and the set difference. And you have your Eisenstein series as this function given by the logarithmic derivative of discriminant function. Okay. And what we know is that set your UAZ to be UAZ. Okay. So just evaluate U at AZ. But a little bit more work will show you that. So this A is a monic polynomial. A little bit more work will show you that you can write this as an infinite series of U. Start with 1, continues with the higher degree terms in U with C infinity coefficients. And with this, in this sense, you have the U expansion given in this way. Okay, you can calculate that the U expansion can be given by this infinite series. And we have all these information, all these results due to Gekeler. And the next one is about the functional equation of it, as you may guess. For any gamma, we have this functional equation given here, that you have this elements, which will be equal to that product times that term with this extra element. just like in the classical case, this is you will have an extra term here. What he proved in 1989 is that it can be seen as the Deligne and Katz results analog. You have your quasi-period defined in this way, f delta 1, 1. Remember, this Drinfeld A module, Pz, was the one generated by Z and 1. So 1 is a period. So evaluate your quasi-periodic function corresponding to that by derivation, taking theta to tau at 1. And then we will see that this Bose-Eisenstein series of Gekeler can be written as the product of power of pi tilde times this h function, h2z, and eta 2z. Okay, so I know there is another term here appearing, and to be honest, I don't know what this h function should stand as an analog in the classical case. But anyway, so that's the identity. That's the identity closest in the analogy with the Deligne and Katz result. All right. So in the next slides, my goal is to show you how we can see this function in the higher rank case. And for this purpose, I will introduce this function ER. Okay. So, okay, the story for the rank 2 case, before I finish it, is there any question about the rank 2 setting? Okay. So basically, what was going on is to what my goal was to show what kind of results we know about the Bose-Eisenstein series in the rank 2 case, so that we can attack and try to generalize them. Okay, so we go back to the rank 2 case, rank R case, when R is arbitrary, and Z is in omega R, and Z tilde is in omega R minus 1 as before. I'm taking this discriminant function and taking the partial derivative of this function. So this can be seen as a function of R minus 1 terms, and I'm considering the partial derivative with respect to Z1, and multiplying with pi tilde inverse and delta R Z inverse, and this is a non-vanishing function. Okay, so I'm defining for any A UAZ by this element. Again, there is no problem of being 0 for this term, because this is not an element or in the kernel of this function. One can expand, just like we do for UAZ in the rank 2 case, that you can expand this as an infinite series in UZ, but this time the coefficients are not going to be constants. Coefficients are going to be weak modular forms on omega R minus 1, but that's perfectly fine. There's no problem with that. And for some nice neighborhood of infinity, Bassan came up with the product expansion for the delta R. And he just generalized the work of Gekeler for the discriminant function, the product formula for the discriminant function in the rank 2 case. And if you use this, we see that we can have a U expansion of the ERZ, very similar to what's happening in the rank 2 case. And this can be stated as like this. All right. So with all this information in hand, now I'm ready to say the first result. So we prove that you have your Z in omega R, and you can actually find the values of ERZ with just in terms of this powers of pi, in terms of the product of this powers of pi tilde, HRZ, and a determinant consisting quasi-periods. Okay, so this is the first main result, and I will just want you to get your attention and take the R equals 2 case. And if you look at the R equals 2 case, this will just nothing but the Gekeler's result. So you have your R equals 2, and this will be the H function of Gekeler in the rank 2 case. Now only quasi-period surviving will be this one, F delta R minus 1, but ZR with our normalization is 1, then you get the Gekeler's result. Okay, so this can be seen as a generalization of what he did. And but the proof is not the same as Gekeler's. Although we used some of the analysis he used in his paper, he proved that theorem for the rank 2 case. But the main object we use is the deformation of the Drinfeld modular forms in the higher rank setting. So for the rank 2 case, this deformation has been introduced by Pellerin. And for the higher rank setting, the first one who introduced is the Perkins in 2014. And we use these ideas and were able to prove that result in the higher rank case. And it turns out that these deformations were quite useful to see how things are behaving even in the higher rank case. Okay, so let me briefly sketch the proof. And let me check the time. Okay, so I'm almost out of time, but I will be quick. Okay, so the sketch is as follows. So you will first define the Eisenstein series in the t-valued Eisenstein series. They are t-valued. Okay, so this will converge in the Theta algebra with respect to the Gauss norm I defined. And this will be this column matrix whose coefficients are these infinite sums. Okay, and as you say, you're deforming the nominator with A1T. What I mean by A1T, maybe I should say, A1, AR, they are all elements in A. I am just writing T instead of theta in the definition of AIs. That's what I mean by A1T. So this is the object we are going to use, but we will also use this matrix, introducing in this way that it has entries in terms of the Anderson generating functions and their twists. Okay, and as you see, this Z1, ZR. So you have in the first column, in the first row, you have the Anderson generating function with Z1 and its twists and so on and so forth. And it's an element, it's a function, it's a matrix with T coefficients, but actually moreover, it's invertible, but I will not talk about this. So what we found out first, which was the quite important part of the proof, that for any T naught in C infinity, whose norm is less than or equal to 1, you can evaluate the Eisenstein series at T naught. And what you get is this ratio having the powers of phi tilde, HRZ, first twist of omega evaluated T naught, and this row matrix having the J1 cofactors of FCT. Okay, this is a bit strange identity because all of a sudden I start talking about the J1, talk about the cofactors, but the reason is that at some point of the proof, you need to take into consideration of the inverse of F. And once you take this, then you will also need to talk about the cofactors, and some comparison of the entries will give you that cofactors. Okay, but basically what I mean by CJ1 T naught is the J1 cofactor of FCT evaluated at T equals T naught. Okay, that's what we mean by that notation. Okay, so, but in the rank 2 case, this was already proved by Pellerin in 2012. But what we do is to enlarge it, is to generalize it to any rank. And now I will use this identity, and then I will, by using this identity, I will define this function, all ER, by the domain is this product space, and then to C infinity, given by this ratio and C11 psi. What I mean by C11 psi is that determinant, because this is the 1,1 cofactor, okay? And this term also appears, okay? You can actually calculate that this will be the cofactor of the 1,1 cofactor of that matrix F. And using that result, actually, that identity I showed you in the previous slide, you can prove that there is a U expansion of this for this element, fixed psi, and then for arbitrarily large Z, you have this U expansion here, okay? And now I will use the result of Pellerin combining the quasi-periods in the left side to the specialization of the Anderson generating function. If I use this, now this determinants evaluating at theta will be just the quasi-periods. And you have also this identity, which I defined earlier. Pi tilde will be equal to first twist of omega evaluated at theta times -1. And what we know is ERZ theta will be AUAZ from here. But this is the U expansion gives you that this is ERZ. And then you have this identity coming from here. And what you have here is, again, from the Pellerin's result, that you have the quasi-periods as the entries of the matrix. And using the connectedness of omega r, now you can say that this function has to be the function we are talking about, and this will finish the book. Okay, basically what we are doing is that idea. And as I say, the main part was actually proving that identity between the Eisenstein series and the Anderson genetic functions. Okay. So the next thing I will talk is the functional equation of ER. So we can expect having a functional equation in this setting because we have a functional equation in the rank 2 case. But it turns out that the functional equation in this setting is quite strange. There are some functions involving when the rank is bigger than 2. So you have your J, and we define this function sending Z to that element. By I mean by Cj1 theta is the J1 cofactor of FZT evaluated at T equals theta. And you have this ratio. And what we proved is that for any gamma and Z in omega r, we have that this element will be product of these times this summation plus this extra term. Okay, so Z1, Z2 are entries of Z, but what is Z1, C11, C1R, or C12, or in general C1J? They are actually 1J cofactor of gamma. Okay, again, cofactors are into play. And this is actually quite strange when we first find out this, because these all cofactors are involving and this interesting functions appearing. We are still trying to investigate what we can expect or what kind of arithmetic information we could expect from these functions for the rank 3 or higher case. But we are interpreting things in terms of this cofactor when it comes to the functional equation. And it's quite strange that, like, if you just go back to the rank 2 case, you get the same functional equation, certainly. But in terms of this cofactor language, I should say, so you have your gamma. I'm turning back to the rank 2 case. Then the 1,1 cofactor is D, and the 1,2 cofactor is minus C. And then if you just apply these to that functional equation, you will get this. And use this identification of omega 2 with the C infinity minus K infinity, then you get what Gekeler got in his paper. Okay, so in other words, I'm saying that this functional equation, all functional equation of involving these cofactors in our setting can be compared to the ones already known by interpreting everything known in terms of this cofactor language. I mean, what I mean by cofactor language is, of course, like just see the elements, see the cofactors, and understand their importance in the functional equation. Okay, so before I finish, I will just talk about this and pass to the transcendental result. So the relation between ER and ERJ is also quite interesting. We don't know much about this ERJ actually, but what we know is that you can also relate the values to relate values of ER to ERJ. So consider this vector with this matrix, whose column, so the diagonals are 1, and you have a 1 in the jth entry of the first column. By this, you can calculate the cofactors as zeros, and the only cofactor surviving is C11 and C1J. And then the functional equation implies that you have ER gamma JZ can be written as ERZ plus ERJZ. Okay, so in other words, ERJZs will be just you can interpret these values in terms of the values of ER function, although the definition is it looks different than the definition of ER. So although in terms of definitions, you can see a certain relation between these two values. Okay. So this is the last thing about the functional equation. And before I finish, let me talk about the last result we have. So I will remind you that a Drinfeld module has Cm if the dimension of this tensor over K, which is actually a field, is R, and we call phi a CM Drinfeld A module. Okay, this was the definition we get. But I will now define the CM points in the omega R for the omega R for the space omega R. So you have your Z in omega R, and we call Z a CM point if the Drinfeld A module phi Z corresponding to the A lattice ZA is a CM Drinfeld A module. Okay, so that's our definition. And what we found out is that you have your Z as the and it's a CM point, and let K bar be the algebraic closure of K in C infinity. Then, if this element is not a zero of false Eisenstein, I shouldn't say false Eisenstein series. If this is not a zero of ER, then it's transcendental over K bar. Okay, and so in the rank 2 case, this is already known due to Chang, that he proved that this theorem holds for the false Eisenstein series of Gekeler. Actually, he did it more than the false Eisenstein series. He did this for the Drinfeld, some certain Drinfeld quasi-modular forms. I should say some certain Drinfeld quasi-modular forms, which are defined in terms of their U expansion. Okay. And lastly, I should say that the proof uses our first result that I said in the relation between the quasi-periods and the ER, the values of ER, and as well as the Chang and Papanikola's transcendence theory, which was also useful to prove the result in the rank 2 case for Chang. Okay, so now I should stop, and thank you for your attention and thank you for listening. Is there any question?
Yeah, maybe I'd like to ask a question.
Yeah.
So this false Eisenstein series, I guess, could be defined not just for theta, but for other elements in FQ theta as well, right? I mean,
the
delta,
false Eisenstein is defined for.
I mean, this delta R is the highest coefficient of
yes,
phi t.
Yes.
Phi theta.
Yes. Yes.
And one could also look at highest coefficients of phi a for other elements in FQ theta.
I see. So yeah, definition I know, and definition we were following is the one which is given by the art coefficient of the image of theta.
Right.
Yeah. Are you saying that there is also false Eisenstein series you can define with respect to the image of theta?
This definition would also work for general element in for general element A in FQ theta, and also actually for more general A, not just the polynomial one. So,
yeah.
But I don't know if people consider this. So, and also HR, I think for FQ theta should make, at least for this case, HR should make sense.
Yeah, I think so. For the HR, as you say, the definition might be more general than this. But for the sake of this work, our target was to focus on that Eisenstein series defined by Gekeler in this FQ theta. Yeah, and then this way the analogies were quite striking. But yeah, this would be interesting to also consider that false Eisenstein series coming from the. Anyway.
I mean, one can wonder whether this functional equation holds for for other false Eisenstein series or
yes. Yeah, I mean, I haven't seen any work in that direction for the rank 2 case, but that will be interesting. Like in the rank 2 case, the false Eisenstein series, I know they were always considering this because they are also important to the theory of quasi-modular forms, as you know, because they are just algebraically independent and some other certain modular forms, which gives you the whole space. But this other, yeah.
Does Geckler only consider this case, or more general?
Yes.
Okay.
Yeah, I think in his Invention paper he considered that.
Okay. Okay. I think his theorem isomorphism is for general A, if I'm not mistaken.
Yeah, of course. Yeah, it's for general A. You're right. For the general definition of the Drinfeld A module, A doesn't have to be the polynomial thing. A can be any, this space of regular functions away from this specific place. Yeah, you're right.
Thanks a lot. Also for your talk.
Thanks.
I have a question,
Yes.
maybe not very related, because this is my first accident with the Drinfeld A modules. What is the relation between Drinfeld A modules and, for example, formal A module laws, Lubin-Tate formal A module laws, for example? Is there an analogy between them, or there is no one?
Yeah, I'm not sure. So these are we can see them as the analog of elliptic curves. I think this will be much simpler. And if you talk about abelian, we have structures called T modules, which can replace with them in the function field case. But for the structure you mentioned, that I don't know. But it's a good question.
Thanks. Because, for example, Lubin-Tate formal A modules, A module laws, I mean, formal group laws or formal A module laws can be defined by two variable formal power series, and maps between them are power series also, and maybe there is some analogies, because
I'm sure.
also you said that there is these are in some sense analogous of elliptic curves, and also formal group laws can define formal groups, and formal groups in some sense are analogous to elliptic curves. In some sense,
yes,
they are formal group
I'm
schemes.
Sure. Yeah, I'm sure they exist, and I kind of remember such a analogy also exists, but I don't want to say something wrong. So, but
I see.
It should exist. I think such a analogy should exist.
Yeah, very, very nice. Thank you.
Okay. If there are no more questions, then let's thank Oğuz Gezmiş again for this beautiful talk.
Thank you.
And these webinars, we're going to have a summer break for the next month or so, and we will send an email when we start having the seminars again. This will be in fall, probably in September. Okay, thanks. Thank you, everyone. And I'm stopping recording.